Okay, guys, you may have heard in lab we're doing a review. We're not doing the TLC lab. We'll be doing that next week. This afternoon at 2:30 we'll be downstairs and we'll have some review time. Please bring your workbook and all your questions. Okay, I have some things to return. Quizzes from last time. Quizzes range from 10 out of 10 to, I'm not sure what the low was. Seems like it was about a 2 maybe. We'll call those back. If you put a course section on there, I'll call your name here. If not, you can pick it up in office hours. C and D first. Matthew. Here. Jennifer. Here. Deep. Here. Margaret.
Here.
Dakota. Here. Ariane.
Here.
John. Here. Brian. Here. Victoria.
Here.
Nicholas. Here. Sloan. Danielle.
Here.
Doyen.
Here.
Celeste.
Here.
Karen.
Here.
Emily.
Here.
Latia.
Here.
Sanjana. Okay, AB lab sections. Catrice.
Here.
Henry. Here. Austin. Here. Nicholas.
Here.
Kevin.
Here.
Alex.
Here.
Mihak.
Here.
Sarabi. Ananya. Sean. Raj. Lacey. Heather. Meredith. Avila. Samuel. Anna. Ja.
Here.
Elena.
Here.
Queen. Tina.
Here.
Eric.
Here.
Sydney. Clayton.
Here.
Rockman.
Here.
Jacob. Jacob. I have a couple of lab reports. Alex.
Here.
Sean. Samuel. Okay, according to the syllabus, we should be starting new material today. I've also sort of not doing that today. We missed 2 days by video only. It should have been pretty straightforward. Video only. You know, you can watch that multiple times. You can ask questions. You should be able to watch that and cover material. But it was a little bit different from our norm. So I'm going to spend a little time today. We also have some unanswered questions on the alkyne chemistry. Let's look at alkynes. Outline nomenclature, pretty straightforward, yeah? Just like alkenes, alkyne is going to take precedence in terms of numbering. I did an example with, I think, like the fluorine here. Still the alkyne is 3 as opposed to 4, just like with alkene. The reactions, we saw twice the fun. Regioselective addition of HCl to the alkyne to give this product here. It's not stereogenic. But we have an alkene. Alkenes react with HCl, so we can repeat the reaction essentially, and the other chlorine ends up on the same carbon. And we saw resonance there. Yeah, resonance there. And that was the main explanation for why cation here. You get the same answer, I mean, left or right, left because it's substituted, but the key thing here is resonance. Resonance stabilized cation, and then the chlorine comes in and attacks. Any questions about that one? Down below we have elemental halogen, twice the fun. The first addition of the halogen is going to be an anti-addition, and so the bromines are anti, E not Z. So this is stereogenic, in this example. We should understand why the halogens are different. I'm doing these just like with alkenes. Some textbooks maybe do it a little bit differently with alkynes because of a good consideration, but I'm doing it just like alkenes. It's just twice the fun. All right, attack, cation here, back bond, and then the other bromine comes in backside. That's how the two bromines end up anti, right? And then you got an alkene reacting with bromine. You did that in lab. Bromine on each carbon. There's no stereochemistry here. Neither carbon is chiral. There's nothing to show. As long as you have everything connected, it's good to go. Yes, these two carbons are tetrahedral. Yes, one's forward, one's back, but whichever one you want to show. Whenever it doesn't matter, we typically just don't even show the projections. However you want to show it, as long as you've got carbon connected to bromines, and it's going to be good. Just like I said, give me one of your mittens. You wouldn't say which one, because they're both the same. I don't have to specify. But if I said, give me one of your gloves, well, maybe you might then say which one. Or give me your hand. But does it matter which one? Yeah, that's a good question, but in this case it doesn't matter. Okay, hydration of alkynes, give enols, and you don't hydrate again. Instead, the enol undergoes a rearrangement called a tautomerization, and the enol becomes a carbonyl. The pi bond ends up between the C and the O. Keto form, enol form. Process is called tautomerization. The relationship, they're called tautomers. Okay? Same exact formula, just a rearrangement. It's pretty straightforward. You can just do it without the mercury. We'll actually be doing it in the lab without the mercury. Just do your mechanism with the H3O+. If you see mercury, just ignore it. Just know that that's typically often included. Because the mercury 2+ ion is more electrophilic than H+, perhaps you could argue that. And so maybe it does involve a mercuronium ion and then a backside attack. Also with the mercury, it may keep it from rearranging. Because if mercury is the actual reactant and it back bonds, it's not going to rearrange. Where with just proton, you could possibly get a rearrangement if it's a free cation. Because what do we know about carbocations? They're prone to rearranging. So again, just sort of textbook, that's usually included. Because alkynes then do tend to be less reactive than alkenes. Okay, tautomerization can be acid or base catalyzed. We're under acidic conditions here. With the brackets, that means this is formed, but it's not isolated. And sometimes it means it cannot be isolated. It continues on. All this is the conditions for the whole thing. We're under acidic conditions. Thus, this is catalyzed by acid. And the tautomerization is a mechanism can be remembered by Oreo. Under acidic conditions, the first O is on because we've got protons. We put a proton on. We've got an alkene. I did this mechanism in the video. This attacks. Where do we want to put a new H? Basically, tautomerization is the key thing here. There's a new H here, yeah. There's 2 there. Now there's 3. There's a new one. And this H has been removed. Essentially, one H has been relocated. No other atoms have been moved if you look at it. One H has been relocated, and that's it. Now, also a pi bond has been relocated from between the carbons to between the C and the O. This is the definition of tautomers, as written up top. Relocation of one H, and then at least one pi bond. It could be multiple pi bonds. Most common tautomers you'll see in introductory organic chemistry is your enol and keto tautomers. Keto also, it could be an aldehyde. You could broaden that out and just call it a carbonyl tautomer. We could also call this an OH tautomer and call that a CH tautomer. Okay, let's see. Which of the following are tautomers of the compound in the box? How are we doing that? The first three are all tautomers of the one in the box. The last one is not. The first three are all tautomers of the one in the box. For example, look at the third one, which I said is a tautomer. Why is it a tautomer? What's the difference? Pi bond has been relocated, if I agree. Okay. Has only one H moved. Well, this N carbon has two H's. How many is on this N carbon? There's three there. So one is now there. Where did it come from? Well, usually where the double bond has moved, because now there's one H here, but over here there's how many? Two. Everything else is the same. 3 here, 3 H's here. 1 H here, 1 H here. And going from here to there, one of these H's is now here, and the pi bond has been relocated. That's the definition of tautomer. And you can do that the same for the other three. Okay? Here, one of the H's on the end is now on the oxygen. The double bond has been relocated. First three are all tautomers. How do we do on this? Did you get this? Yeah? The last one is not a tautomer. Why not? Well, you could say because it doesn't meet the definition of tautomers, but specifically, why not?
2 double bonds have been. Oh no, it's at least more than 1 H.
Well, let me ask you this: do tautomers have the same formula?
Yes.
Yeah, that's why I put the formula up top, because you can see that. It's just a rearrangement. It's the same formula. By the way, the question at the bottom, what are tautomers can also be called what? Constitutional isomers. What's the definition of constitutional isomers? Same formula, different connectivity. That's what you have with tautomers. Same formula, different connectivity, because we have reconnected an H and connected it somewhere else. Constitutional isomers, yes. They're not enantiomers, not diastereomers, and they're not resonance structures. I don't say many, but often students will say they're resonance structures. No. When we do resonance, we never move any atoms. Constitutional isomers, same formula. Okay. Are these two constitutional isomers? No. They don't have the same formula. They do not. You could add it up. How do I recognize they don't have the same formula? DUS. I mean, DUS. Do they have the same number of carbons?
Yes.
You can easily see that. 5?
Yeah.
Okay, but do they have, and oxygen, they both have 1, but do they have the same number of H's? You can count them up. But I would do DUS. How many DUS here? 2. How many here?
1.
It would be a different number of H's. It's a difference of 2 H's. This compound has 2 more H's than that one. I'll look at DUS. And since it has more H's, it's not a constitutional isomer, it's not a tautomer. It's a totally different compound that fits none of these definitions. But see, these all have 2 degrees of unsaturation, just like that one. Same number of carbons and thus same number of H's. Again, based on knowing what DUS is. Are these tautomers? Tautomers? Yeah, they are. One H has been relocated. What H has been relocated? Well, obviously the nitrogen has an extra H. But where did it come from? Where's that H at over here? It's right there. But in going to the other structure, it's been removed and relocated to the nitrogen. And how many pi bonds have been relocated? Two. In this case, 2 pi bonds. Yeah, those are tautomers. CH tautomer, you call that an NH tautomer. Up here, this was an OH tautomer, yeah, OH tautomer of that. And this would be another CH tautomer of this. Just the H, the hot potato H, the one that gets bounced around, where is it located? OO, and then that one is on a C. So that's a CH tautomer of this, and that ain't tautomer. Good? Yeah? That's tautomers. We'll see tautomers again in organic 2 when we look specifically at carbonyl chemistry. Okay, over here. We can hydrate an alkyne using hydroboration oxidation, just like an alkene. What do we know about this outcome? It's a hydration, but it's what? Antimicrobial hydration, yes. Instead of the water or the oxygen bonding here, because that's where the cation might be, the oxygen is going to end up bonding over here on the N carbon. That's why I got the oxygen here. So mechanistically, we can get to that hydration product. This is an enol. What do we know about enols? Typically not stable. An enol is going to tautomerize to the carbonyl form. So, can you draw the carbonyl? Basically, the double bond is going to come be here now, all right. And this H is going to end up where? It actually is going to end up on this carbon, because if we draw the double bond instead between the carbon and O, well, this carbon doesn't have a bond anymore, the extra bond. We removed the bond here. So instead of that being double bonded, we've got to have a bond, and what's the bond to? It's now to that H. Well, it's now there. I can just leave it like that. There's one H, but now how many are on that carbon? 2. It's a plain line bond structure, which implies 2 H's. There it is. But it looks naked to me, because that's what functional group? It's an aldehyde. I prefer to draw in the H of the aldehyde. The H is on the carbonyl. Now, confusion alert. But that's not the H that was relocated in the tautomerization. No, it's not. That's the H of the aldehyde, which I've always said I like to draw in, because, all right? Here, tautomerization gives the carbonyl form, but the carbonyl form is actually an aldehyde in this case. Is there anything to remember? If you hydrate with BH3, do you always get aldehydes? No, I don't think so. If you do a tautomerization under basic conditions, do you get an aldehyde? No, I don't think so, not always. It just happens to be an aldehyde in this case. So don't overthink it and try to make too many assumptions. Or too many incorrect assumptions. Assumptions are good. Actually, assumptions are good. That's what we want to do. We want to use our knowledge and then apply it. You're making an assumption, an informed assumption. Sometimes you guys make assumptions that aren't right. Or try to connect things that really aren't connected. Yeah, it's an aldehyde. Base catalyzed tautomerization. I think we can maybe do that. There's been a number of questions, so let's give it a try. We're under basic conditions. When this is formed, we're under basic conditions. It's not formed until we add the magic step. After BH3, there's a boron. Then we put this in, and you get the enol, but it keeps going. And we're under basic conditions. And bases, do they add H's or remove H's? They remove them. That's why the first step of Oreo is off. What H do we want to take off? The one that needs to be removed. The H needs to be removed from the oxygen. Let's take it off. We always need to have a bond when we're doing mechanisms. Let's draw a bond here. And we have hydroxide. These electrons take the H. These electrons stay behind. And we get this anion because there's two lone pairs there. Good old acid-base mechanism. Like any other Bronsted-Lowry acid-base mechanism. Is this acidic enough? What is the equilibrium? Those are all good questions, but they really don't need to be asked because we got to do this. Really, though, I'm wondering, I mean, anything can act as an acid. Again, what is the equilibrium? Can you remove that H? Again, it's a good question, but if the answer is no, then you're not doing a top isomerization. Clearly, you have to remove it if we're going to get to this product. So let's do it, and let's keep going. So we took a proton off. What do you want to do next? Resonance. Okay, this is one reason I tend to not want to do this quite yet, is because the resonance we're going to do here we haven't seen before. We typically have positives and we move electrons in. I'm going to do this, but we're really not going to cover this till after the test. This is all the electrons in, electrons out. These electrons can move in. These electrons move out onto the carbon. What does that arrow movement give? Now that you should be able to show. You may not be able to come up with the arrows, but once I show them, now you should be able to show what these arrows give. What's now between the C and the O? These move in to make another bond. It's going to be a pi bond. How many lone pairs left on oxygen? 2, because the other one moved in. That's not. Okay. What does this arrow mean to you? Maybe we haven't seen this. These electrons, pi electrons, are moving out just to sit on the carbon as a what? As a lone pair. Yes, that's what that means. And there we go. Of course, resonance structures always have the same net charge. This is an anion. This better be an anion. Where's the minus at? The carbon is now minus because how many H's are on that carbon? 1. 1, 1, still 1. And if there's only 1, that means there's 3 bonds in a lone pair. That's a negative charge. That's a resonance structure because all we did is move pi electrons. We'll talk more about it. But we just did resonance. On the board we did resonance. Now we have this. What do we need to do to get to our final aldehyde culture? Off resonance. On. You got to put a proton on. Where do you want to put it on at? We identified where it was. There's an extra H here. We need to put an H on here. What can supply the H? Yes, water. Right here we made water. That plus water. What can supply the H? The most acidic H around. We've got water. We also may have more hydroxide. Which one's going to supply the H? Water or hydroxide? Water. The most acidic one. Which one's more acidic? This one. You don't want to take an H from there. That'll make it 2 minus. Take an H from water. These electrons take an H from water. Leave this behind. Let's just get rid of hydroxide. What does that give? It gives that. There's now 2 H's there. Plus what? What did we form here? We already had the arrow there. Plus hydroxide. Right, we formed that right here. That's catalyst. Catalyst reformed. That's what we started with. Theoretically, all you need is one molecule of hydroxide. Once it's reformed, you can come back over here and catalyze the next reaction. Off resonance, and then we put a proton on. I've got the H drawn in there. That H is here. One H. There's one H here along the way, everywhere. One H, one H. I just have it drawn in at the end. So that's a base catalyzed tautomerization. I'm sorry I didn't give you a chance to do it on your own.
It's okay. Now I understand now. Thank you.
Okay, reduction of alkynes. We can reduce them down to the alkene. Whenever you add H's, that's reduction in organic chemistry. We can hydrogenate, standard hydrogenation with a metal catalyst. Two H's, we know it comes in syn, right? The H's come from the metal catalyst, like two darts, no mechanism really shown. And so the two H's are going to be on the same side. That's going to push the two methyls to the same side, and thus you're going to have a cis product. You would not get a product with the methyls trans. But this is an alkene. Alkenes can react with the same conditions. We've been doing it for 2 or 3 weeks. And if you react again, you're going to end up with the alkane. Now this has stereochemistry. There's no stereochemistry there. Nothing to show. We can partially reduce it, or we can fully reduce it all the way down to the alkane. We can also say we've saturated it. Partially saturated. Now we've fully saturated our compound. Everybody agree with that terminology? The alkane is a fully saturated hydrocarbon. Can you stop with the alkene? You can if you use a poison catalyst, a catalyst that has been made less reactive. Less reactive by adding a so-called dopant, like a heavy metal, or sometimes amines. Lindlar catalyst is the most common. It makes the catalyst less reactive, and you can actually get it to stop here at the cis alkene. And if you have an alkene, it will not do anything to it. It will not reduce it if you use a poison catalyst. You have to use an actual non-poison or regular catalyst like palladium, platinum, or nickel. Poison catalyst stops it at the alkene and it will not continue. So that becomes a way to make alkenes from alkynes, but the alkene is going to be cis. I mean, we're still doing a hydrogenation, two H's coming from the metal. So it's going to be cis. So we can fully saturate, we can partially saturate or hydrogenate to cis. How can we make a transalkene from an alkyne? We can do a dissolving metal reduction. This is a radical reaction. I think this is our first look at a radical reaction. Fascinating reaction. Sodium, what does sodium like to do chemically? It likes to give up one electron and become sodium plus. A variety of ways it can give up an electron. But really it's, how does sodium give up an electron? What's mechanistically? It needs to give up one electron. Usually we always deal with a pair, either a bonding pair or a lone pair. One electron is going to have a radical. It'll lead to something having an odd number or an unpaired electrons. How does sodium give up an electron? It's usually some type of single electron transfer process, SET. A little bit vague of how that goes on. We say that the sodium becomes oxidized when it loses the electron. It turns out that if you put sodium metal in liquid ammonia, ammonia is a gas at room temperature, but at cold temperature, -33, it will be liquid, and you can actually use liquid ammonia can be your solvent. All right, got to keep it cold. Let it warm up, your solvent's going to evaporate real quick. You put sodium in, and it turns a brilliant blue, the color of these markers. You can find this on YouTube. And the electron is coming out of the sodium, and it's being solvated by the ammonia. You can probably ask some physics questions about it. I mean, will it be conductive, etc. It's a fascinating thing. And who was the first person to put sodium and ammonia and see this color? Had to be somebody along the way, 200, 300 years ago. I don't know, but it's amazing. I know it was. Well, what is that? Well, then maybe 50 years later, we have more knowledge, but somebody did it. And solvate electrons, and then if you throw an alkyne into this mixture, then the electron will actually start becoming reactive and react with this. And I showed the mechanism. The electron pumps in. Usually this is attacking something like this, yeah? These electrons attack. In this case, we have an electron pumping in, coming in here. Why would an electron come in here to electrons? That's a good question. It's kind of counterintuitive. Well, it's a good question. You could think about that, get a cup of coffee, and think about it for a while. I mean, why would two electrons like to come together and make a bond? Electrons should repel. Well, it goes back to that. If they're the right way, they can complement each other and come together. So the electron comes in, it produces an anion, and the anion, we got two H's added. Where did the H's come from? Ammonia is the only source of H's. Ammonia acts as an acid in this reactor. It supplies the H's. I went through this in the video, but you get trans. Why is it trans? Basically because the molecule has a choice. And trans is better. When we hydrogenate, the molecule does not have a choice. The H's come in from one side, and that's it. Any questions? Any questions? So that's a way to make a transalkene from an alkyne. And so you do need to kind of, along the way, catalog your reactions. You got your toolbox, all right? Do you know any other way to make transalkenes? Or for that matter, do you know any other way to make an alkene right now? If you were asked, how do you make alkenes? Tell me a way to make an alkene, what would you say? That's the type of question, because in organic chemistry, one thing is how to make certain functional groups. And that's sort of something you can keep a journal of or your toolbox. Now, during test 3, we'll see other ways to make alkenes. Right now, the only way we know how to make alkenes is the last 2 pages. This way gives transalkenes. If you want a cis-alkene, it's a poison catalyst with hydrogenation. Okay, the last thing here is looking at the acidity of terminal alkynes. The SPCH here, this H has some acidity. We saw that early on with hybridization during test 1. Because the resulting anion is sp, this lone pair is in an sp orbital, 50% s, more s character closer to the nucleus, closer to mama, more stable. So in terms of a hydrocarbon, it's one of the more acidic hydrocarbons you'll see. Now, how acidic is it? Well, it's pKa of 25. How acidic is it? Not that acidic. But it's more acidic than an alkane and an alkene. I mean, water is 16. We don't call water an acid. This is a billion times less acidic than water. Acetic acid is like 5. And then something like HCl is like -5. So, but it's strong, it's acidic enough that we can deprotonate it pretty easily. But you have to use a strong base. Hydroxide won't work. And then we can look at equilibrium. Which side's favored, 25 or 16? Well, the weaker acid, this side's favored. So it's not going to go that way. It's actually coming this way. That is, if you take, what do you want to call this anion? An acetylide anion. If you treat it with water, are these going to react? Yes, it's going to go this way. This will take an H from water. And you'll put the H on, and it's coming this way. This side is favored by 10 to the 9, a billion. This side's favored. If you treat acetylide anion with water, you're going to put the H on. If you treat this with hydroxide, it ain't going to go that way too much. The equilibrium looks like this. That way's favored, the other side is like this. I would have drawn it even smaller, but then you wouldn't be able to see anything. All right? But up here, that side's favored because we're using much stronger bases. Hopefully you can tell that that's a stronger base. We talked about that during week test 1. These are strong bases. This one is good in practice. That one's terrible in practice. But it's common in textbooks. So we can make them using these bases. This is important because the reverse reaction is actually used in a very old-timey application. Miners' helmets. Back in the 1800s, miners used to wear helmets with a flame up here. So when they looked somewhere, the flame would illuminate what they're looking at because they didn't have battery flashlights. Or a handheld lantern with a flame. But was the flame, was there some type of gas or whatever? Well, actually, yeah. What they did is calcium carbide, which can be made from like calcium oxide plus carbon or something probably. And these are sort of like ores. This is old classical, 500,000-year-old chemistry. This can be made. If you take this is a solid, and treat it with water, what's going to happen? Well, we just described what will happen. Because calcium carbide is structure, it's the calcium salt of the dianion here. Both carbons are anions. Okay? Treat this with water, what's going to happen? We're going to put an H on each end. Just like we showed coming in reverse. And an H on each end, we now have this molecule here, which is what? Acetylene. And if you know, anybody knows acetylene, ever used acetylene or where it's used at? Torches, acetylene torches, high-burning, high-temperature torches. It's a flammable gas they can use to create a flame. And so in the contraption there's two compartments. One is with the carbide solid and then water, and somehow they come together, produce this, and it comes out the port and you light it. There's a video, I think, on my YouTube page that is linked, which kind of shows this. You guys seen that video? Because it's kind of a little funny at the end. Anybody seen it? Nobody saw it? Okay, a little bit funny at the end. But it's a guy showing a kind of a rusted can with a light. It's old. And he actually puts the carbide in there and puts the water in there and shows how it puts the lid on and then lights the match. It's amazing it doesn't just blow up, but it's all controlled. And it's just like the gas in your grill is controlled to come through when you light it, it flows. And it generates the gas sort of in situ inside the container by this chemical reaction. And it doesn't have to be magic. It can be understood. Right? Now, the acetylide anions, we will use them during test 3 because there will be good nucleophiles. And during test 3, I'll say, remember how we generated them. And you will go, don't do that. Right here. We generated them right here. Okay, I went through that pretty quick. We've got 5 minutes for questions. Pretty good, yeah. What were major questions here? We looked at tautomerization a little bit, yeah.
So, hydration of the alkynes, hydroboration and oxidation. The pi electrons move to the carbon, and then we create a resonance with the electrons from the oxygen double bond.
You mean when it reacted to pH 3?
Right.
What do you mean?
It's in the second step. This is after hydroxide has already taken the H.
You mean the tautomerization?
Right.
Okay.
And
We haven't done that type of resonance yet. It's the first time you've ever seen that. Did I say in and out? We'll be doing that next week. And on Monday, I'll give you a handout for test 3 material. We'll begin test 3 material on Monday. And that's why I'm hesitant to show that resonance. The resonance we showed with the previous earlier reactions on this handout, we've kind of seen. Electrons moving in, the cation. The resonance we saw here is sort of newer to us. What we're doing. You said the electrons move in.
the pi electrons from no bond move to the carbon. And
Yeah.
they're a lone pair. You
They
sit
move.
there.
They move. Here's a double bond.
Right.
Something comes in here, and something has to leave that carbon. So these electrons, we moved them back over here,
Right.
sort of as a lone pair.
But usually, when we remove those, why not just bond them straight to the hydrogen? Because usually because it's going to end up doing that anyway.
All right, let's go back.
You know what I
here.
mean?
Let's see where we were. We had an anion, I think.
On oxygen.
Yeah.
Just like that.
And you want to do what?
And we drew an arrow
Yeah,
showing.
these came in and these moved out. and became a
Right.
lone
So
pair.
why not just bond straight to the H? Is it just
Bond what to the alkene?
right?
We don't have an H. What H would you bond it to?
Well, we made water, and you said we could use.
Right,
that.
we made this plus water. You want to react that with water? Keep in mind, we said it early on, alkenes don't react with pure water. The skin of an apple is largely alkenes, and the skin of the apple protects the inside from rain.
So that's the reason we have that.
We do not have H plus here. If we had H plus, we could have the alkene attack the H plus. We don't have H
I
plus.
got you.
Water is not electrophilic enough. But we also have resonance. And resonance is there already. Resonance is not a step in chemical life. Resonance is a step of us on the board. These electrons move in. By the way, we cannot just move them in, because if we just move them in, now we have that, right? If I just move these in, but there's an H here. And now I've got 5 bonds to carbon. And that ain't no good. So I move these in, but I move these out at the same time. So these move out and become a lone pair here, and that's a minus. That's resonance. That's there as soon as it's there. So we can't not consider that. As soon as this is formed, it forms a pink color. My first structure, though, is red. And this one's white. As soon as this reacts, as soon as this takes off, you get a pink. That's because what you really get is a blend of these. We can't ignore the blend ever. So in practice on our paper, you need to go ahead and show the residence. That's one answer. The other answer is, like we've already said, there's no H+, and alkenes are not going to react with water. Good question.
Yeah. Is it possible for the pi electrons on the enol to move into the oxygen, kick off the H, and that H bond to the carbon cation? Or would that be just completely not?
These move here.
Yes,
The old windshield wiper?
yes, sir. And then
terminology?
kick off the H, and the H would take the resulting carbon cation.
And then take these and move these off?
Yeah, kick off the H, and the H could bond back to the carbon cation. Is that possible?
The main problem there is, okay, in terms of arrow movement, the arrow movement would be reasonable. That arrow movement would give double bond to O,
But that's just not reactive enough.
2 here. This would be cation, and what do we generate?
An H.
H what? That's an H, but it has a lone pair, right? Right? And that's H minus. And now you want to add this in here?
Yeah.
That would give you your product. That ain't the mechanism, though.
Okay.
Mainly because you're not going to create H minus.
Okay.
Um,
Because
I mean, H would have to take the electron from oxygen.
Do what?
Just because H would have to take the electron from oxygen, is that the main reason?
Yeah, I mean, you got
Yeah.
difference in electronegativity, H minus. But just in terms of arrow movement, that's semi-reasonable, but I'm not going to make H minus almost never in this class. There's one reaction where also, we know that this reaction is catalyzed by hydroxide.
and the hydroxide reaction.
And in your mechanism, you're not showing hydroxide doing anything. So you're not utilizing all the information we know. We know that if you add hydroxide, the tautomerization equilibrium is faster achieved. So you need to account for that in your mechanism. Just like you need to account for stereochemistry in your mechanism. Good. Okay, guys. This afternoon, 2:30 downstairs. Quiz on Monday, and then we'll move into new material. Quiz on Monday will pretty much be on just about anything. The test is the following day. Should be pretty straightforward. Have a good weekend. Good news is Georgia will not lose this weekend.